Okay, I'm going to begin section 3.4 and 3.5. I've kind of got these combined, although most of the information is in 3.4. But what we're going to talk about is measures of position, and really that's kind of just fancy words for two things, which are z-scores and percentiles. Okay, and then in 3.5 we'll talk about box plots, which is another illustration that you could make in statistics class. All right, we'll start off with the z-scores here first. A z-score represents the distance that a data value x is from the mean in terms of the number of standard deviations. Okay, and just like some of this other stuff here, we've got population z-scores and sample z-scores. Now the formula is the same. It's just making sure you got the right symbol. Okay, so when you find a population z-score, it's going to be x minus mu over sigma. When you find a sample z-score, it's going to be x minus x bar over s. Okay, now z-scores are going to be important later on once we get to the normal distribution, which is chapter 7. Pretty much everything that I'm going to talk about, from chapter 7 on, it has to do with z-scores. Okay, so z-scores will be super important later on. If a data value is larger than the mean, the z-score is positive. If a data value is smaller than the mean, the z-score is negative. Okay, so positive, negative doesn't mean good or bad. Okay, if the data value equals the mean, the z-score is 0. Okay, for example, a z-score of 1.24 means that the data value is 1.24 standard deviations above the mean. A z-score of negative 2.31 means that the data value is 2.31 standard deviations below the mean. Okay, so you're above the mean or below the mean. Let's take a look at some examples here. So problem 10 says that you're filling out an application for college. The application requests either your ACT or SAT score. You scored a 26 on the ACT composite and a 663 on the SAT. On the ACT exam, the composite mean score is 21 with a standard deviation of 5, while the SAT has a mean score of 514 with a standard deviation of 113. Which test score should you provide on the application and why? Okay, so the way that we got to do this is we got to compute z-scores. Okay, one for the ACT and one for the SAT. So to find a z-score, you take your x value minus the mean divided by the standard deviation. Okay, so with the ACT, it says you scored a 26 on the ACT composite, that'd be the x value. The mean score is 21, that'd be mu. And the standard deviation is 5, that'd be sigma. Okay, so 26 minus 21 is 5. 5 divided by 5 is 1. Okay, so we got a z-score of 1. Now what that means to us is that we're going to have to move out one standard deviation. The standard deviation is 5. So one increment of 5 units to get from 21 to 26. I think that should make total sense to us. Okay, so if I'm sitting at the mean, 21, and I need to know how to go to 26, well, I got to go 5 units to the right to make that happen, or one standard deviation. To find the z-score for the SAT, it's similar, or it's the same formula. So it says that you scored a 663 on the SAT, so that'd be the x value, and the mean score on the SAT was a 514 with a standard deviation of 113. Okay, so when I enter that in, 663 minus 514 divided by 113, I'm looking at about 1.32. Okay, if I go nearest 2 digits on that. By the way, whenever you guys work with z-scores, unless you're told otherwise, always round those values to 2 places. And the reason why is because of this table that we're going to use later on in chapter 7. when we talk about the normal distribution. So the table, it has a bunch of z-scores on it, and those numbers are all rounded to 2 digits. Okay, is the reason why. So what this means is that we're going to have to move out 1.32 standard deviations. Now the standard deviation for this guy here is 113. Okay, to get from 514 to 663. Okay, so let's see, I need to move out a little bit more than one standard deviation, about 1.32 standard deviations to get from 514 to 663. Okay. Now, which test score should you provide on the application? Well, let's see, the SAT score had a bigger z-score, so it's relatively better. Okay, now, but both scores you were positive, right? So you did above the average on both tests. It's just if you're going to provide this on an application to a college, is the one for the SAT is going to make it look better, since that had the bigger z-score on it. Okay, so I want to use the SAT because it's relatively better. Okay. Problem 11 says that the average 20 to 29-year-old man is 69.9 inches tall with a standard deviation of 3 inches, while the average 20 to 29-year-old woman is 64.6 inches tall with a standard deviation of 2.8 inches. Who is relatively taller, a 67-inch man or a 62-inch woman? Okay, well, a quick comparison would be to say that the man is taller, okay, duh, because 67 is bigger than 62. But comparing it this way would be kind of unfair, since it's a proven fact that men are generally taller than women. Okay, so rather than comparing the man to the woman, let's compare the man to all the other men and the woman to all the other women, and we'll see who's taller relative to their gender. Okay, now to do that, we need to compute z-scores, one for the man and one for the woman. So let's see, the one for the man is 67 inches tall. Okay, so that'd be my x value. And 69.9 inches is the average for this age group. And the standard deviation is 3 inches. Okay, so when I compute this here, 67 minus 69.9 divided by 3, I get approximately negative 0.97. Okay, then find the z-score for the woman. Okay, now she is 62 inches tall, so that would be my x value. And the average height for all the women in this age group is 64.6 inches. And the standard deviation is 2.8 inches. Okay, so when I compute her z-score, I get roughly negative 0.93. Okay, so who's taller? Well, so but by the way, since both these z-scores are negative, that means that both the man and the woman are less than the average height of their respective genders. Okay, it's just the woman is going to be relatively taller since the man is further less than the mean, further less than 0. Okay, if I compare negative 0.97 to negative 0.93, negative 0.93 is bigger. Okay, so the man is going to be farther below the average than the woman would be. Okay. Problem 12, the 2013 World Series featured the National League champion St. Louis Cardinals against the American League champion Boston Red Sox. During the regular season that year, the Cardinals scored 783 runs, and the mean number of runs scored in the National League was 648.7 runs, roughly, and the standard deviation was roughly 58.6 runs. The Red Sox scored 853 runs, and the mean number of runs scored in the American League was roughly 701.7 runs. The standard deviation was roughly 73.1 runs. Okay, which team had the better run-producing season? Well, again, a quick comparison would be to say that the Red Sox were better because, they scored more runs, right? So 853 is way more than 783, okay? But it would be kind of unfair to compare, the Red Sox to the Cardinals, since the teams play in different leagues. Okay, the Red Sox play in the American League and the Cardinals play in the National League. So the only time that these two teams played each other was during the World Series. So it wouldn't really be fair to compare, the Cardinals to the Red Sox if they only play each other, one time in the World Series. Okay, so it'd be better for us to compare the Red Sox to all the other teams in the American League and the Cardinals to all the other teams in the National League, and who did better relative to their league. Okay, well, let's see. The Red Sox scored 853 runs, and the mean number of runs in the American League was 701.7 runs, and the standard deviation was 73.1 runs. Okay, so when you enter that into the calculator, the z-score for the Red Sox was 2.07 roughly. Okay, again, if I go nearest two digits. The one for the Cardinals, so the Cardinals scored 783 runs, and the mean number of runs scored in the National League was 648.7, and the standard deviation was 58.6. Okay, and by the way, just a note. So notice how the data is way more spread out in the American League than it is in the National League. How do I know that? Well, it's because the bigger standard deviation. Remember, the bigger the standard deviation, the more spread in the values. The smaller the standard deviation, the less the spread. Okay. Now, if I compute the z-score for the Cardinals, they had a z-score of roughly 2.29. Okay, so who did better relative to their league? Well, but by the way, both the Red Sox and the Cardinals did great that year. Okay, since their z-scores are both positive values, and so they're pretty far above the average in their respective leagues. And the average is 0. Okay, it's just the Cardinals had a relatively better run-producing season since their z-score would be higher than the one for the Red Sox. Okay. Now, let's see here. Another. Let me read a definition. The kth percentile of a data set is a number which we're going to call p sub k, such that k% of the observations are less than or equal to p sub k. Okay, so in these three statements here, we're just going to give an explanation about what each statement means. Okay, problem 13 is where we're looking at the 20th percentile of the height of females 3 years of age, and that is 36.1 inches. Okay, so what that means is that 20% of females 3 years of age have a height that is 36.1 inches or less. Okay, and by the way, there's a couple of things that I'm looking for when you give an explanation like this. So number one is make sure that you're including everything. So like I wouldn't say 20% of females have a height that is 36.1 inches or less. That's not true, right? So females means that they're 0 to way over 3. Okay, no, I'm only looking at 3-year-olds. Okay, so it is important that I state the age. And mention the height, mention all the key things there. So now what I see sometimes students do is they'll say 20% of females 3 years of age have a height that is 36.1 inches, period. No, that's not true. Okay, So a percentile rank is always a number such that k% of the data values are less than or equal to p sub k. Okay, so you should always be stating this as a less than or equal to situation, not an equal to situation, okay, but always a less than or equal to. Let's look at problem 14. The 98th percentile of IQ scores is 133. Okay, what does that mean? It means that 98% of IQ scores are less than or equal to 133. Again, less than or equal. Okay. Problem 15. A 3 to 5 month old male child who weighs 14.3 pounds is at the 17th percentile rank. Okay, so what does that mean? It means that 17% of 3 to 5 month old males weigh 14.3 pounds or less. Okay, again, stated as a less than or equal to situation. And be specific, be specific. So include the age, include the gender, okay? We're talking about weights, right? Now, don't confuse a percentile rank with a percent. Those are two completely different things. Okay, if you score a 75% on the test, are you in the 75th percentile rank? Probably not. Okay, because what the 75th percentile rank means is that 75% of the data values are going to be less than or equal to p sub k, whatever number that is. So, on a particular test, you could have a score of like an 87% be the 75th percentile rank, or a 62% be the 75th percentile rank. Okay, 75% and 75th percentile are two totally different things. Okay. All right, we'll go ahead and stop it right there, and I'll pick with this then in the next video.